Hello everyone. Welcome to the lecture on convolution integral. In this lecture, we are going to see how we can convolve an infinite duration signal with a finite duration signal in continuous time domain. So the example which is being taken is a unit step u of t convolved with h of t, which is 1 for t defined between 1 to 3 and 0 elsewhere. So in the earlier lecture, we have discussed how we can convolve two infinite duration signals. We have seen that there were two cases, t greater than or equal to 0 and t less than 0. In today's lecture, we are going to see how we can convolve an infinite duration, that is u of t is an infinite duration signal, with h of t, which is finite duration signal. You can observe that h of t is defined only between the interval 1 to 3 and it is 0 elsewhere. So this kind of question involves one or two more cases extra when compared to the earlier question which had only two cases. So let us see how we can compute y of t for such a kind of a question. So initially we start with the definition of convolution, which is defined as y of t is equal to integral minus infinity to plus infinity x of tau h of t minus tau d tau. So this is how we define convolution integral in continuous time domain when the signals x and h are continuous time signals. So as discussed in the earlier lecture, we summarize the operations once again involved in convolution integral. The first operation is that we are going to sketch x of tau and h of tau, then fold the signal h of tau, shift it and multiply. We are actually multiplying here, we will multiply here, and after multiplying, what we do is we will integrate and determine y of t. So the basic operations are folding, shifting, multiplication, and then integration. So these are the four basic operations which are involved in convolution. So let us start with the first step. You can observe the very first step here is to sketch x of tau. So let us sketch x of tau. That is the first signal. So x of tau was nothing but a unit, or x of t was nothing but a unit step signal. Unit step. So unit step, which is 1 for all values of t greater than or equal to 0 and 0 for all values of t less than 0. The t is actually replaced by a dummy variable called tau. So here the tau is the dummy variable. So we have sketched x of tau as the very first step. So after we have sketched x of tau, the next step, let us go back to the equation and check it out. So the next step is to time reverse or fold the h of tau. So to do it, first let us sketch h of tau. So we will again revisit the equation of h of tau, which was on the earlier slide. H of tau was of amplitude 1 for all values of t between 1 to 3, 1 to 3 and 0 elsewhere. The tau is the dummy variable, in the t is replaced by tau, which is a dummy variable. So it is 0 for all values of for all other values. It is only defined between 1 to 3. So here goes our h of tau. So once we have determined h of tau, the next step is to get the time reversed signal, that is h of minus tau. So in the next slide, we have h of minus tau. We have flipped this signal. We have flipped this signal over the vertical axis, and we have sketched what is h of minus tau. This is clear as we have already discussed operations on signals. -1 and -3. And this is our h of minus tau. So this is our step 3. So once we have time reversed or folded the h of tau, the next step is to compute h of t minus tau or shift the time reversed signal. We are going to shift the time reversed. So the step 4, h of t minus tau is what we have to compute. T minus tau is what we have to determine. So in the process, we have sketched h of t minus tau. You can just see that I have replaced t by, we had -1 and -3 in our h of minus tau. I have written a generalized expression for the sides of the rectangular pulse, that is t minus 1 and t minus 3. This is how we have written. Now let us check if we are actually right in writing these expressions. If I substitute t is equal to 0, it is -1 and -3. That is when the signal is not shifted at all. When the signal is not shifted at all, we end up getting the same uh, indices. That is the same index we get. So -1 and -3. So we can think of this t, which what are the different values of t, that we will see case by case in the subsequent discussion. So we are bothered about what value of t are we interested in. This t we are actually fixing it up. So the rectangular pulse, the sides of the rectangular pulse we have written t minus 1 and t minus 3. These are the two limits, t minus 1 and t minus 3 on the time axis. So we have given these limits. Now these play a very important role in determining the subsequent cases. So let us see how they are. So first case is that now when this t minus 1 is less than 0, I'm fixing a limit because there is our u of tau is defined for all values of tau greater than or equal to 0. Now we are fixing a limit that this t minus 1 is any value, that is I'm shifting, let this edge be anywhere less than 0, less than 0. So what if it is less than 0? So to get a better understanding, we have both the signals on the same graph, x of tau, that is computing the product x of tau with h of t minus tau. We have both of them together. So you see that for when t minus 1 is less than or equal to 0, that is when this edge is shifted to any limit which is less than or equal to 0, do we see a product between x of tau and h of t minus tau? This is our h of t minus tau. Do we see a product? No. So x of tau and h of t minus tau becomes 0. So the integral on evaluation of this for this particular case, that is t minus 1 is less than or equal to 0 or t is less than or equal to 1, becomes 0 because there is no product which exists in this case. So once again, I would like to summarize that we have taken a case where t minus 1, this edge, is less than 0. So in such a case, there is no product which exists. So we end up getting for case 1, the y of t is 0. Case, we will slowly slide that edge to the right side. We are slowly sliding that particular edge to the right side. So we see that this edge has been, the rectangular pulse is slowly slided towards the right side where the signal is persistent. The signal is persistent in this particular region where it is defined for all values. X of tau is defined for all values of tau greater than or equal to 0. We slowly glide it towards the right side where the signal is actually existing. So you see that we have slided in the case 2. Now how do we mathematically write this particular part? So we fix it up that t minus 1, which was our edge, that is greater than 0. Now we have taken up, it has crossed our 0. T minus 1 is greater than 0 or we can also write that t is greater than 1. And another thing, we are fixing on the other limit. What is the other limit? The other limit is stating that the other edge of the signal, that is t minus 3, is less than 0. We are saying that this is t minus 3, t minus 3 is actually less than 0. So it is on the negative side, on the negative side. So t minus 3 is less than or equal to 0 means t is less than or equal to 3. So superimposing the x of tau and h of t minus tau on the same graph, we will see that in this case there is a product which actually exists between 0 to t minus 1. So where is the product which exists? The product here exists for the region 0 to t minus 1, or we see an overlap 0 to t minus 1. And of course, there is no change in the amplitude of the signal. The rectangular pulse was also of amplitude 1 and the unit step is also of amplitude 1. If at all they were of different amplitudes, we should have bothered about it by accordingly multiplying. But in this case, both of them remain 1. And the interesting thing is to bother about the product which exists. They exist in the region between 0 to t minus 1. Now coming to, this was graphically depicted. Now let us see how we can do it mathematically. So y of t is equal to integral minus infinity to plus infinity x of tau h of t minus tau d tau. This was our expression. Now we have to bother about the product which is existing between 0 to t minus 1. So the product is 0 to t minus 1. The limits changed and of amplitude 1 d tau. On integrating, we will get t minus 1. On substituting the limits, we will get t minus 1 as the answer for the second case, case 2, wherein we have slowly glided the rectangular pulse to the right side. Now the next case is that the width of the pulse was 3. The width of the pulse was 3. Partly it was on the positive side and partly the pulse was on the negative side. Now the next case, an interesting case, is that we are going to glide the rectangular pulse completely to in the positive side. So the edges, that is t minus 1 is definitely greater than 0. That remains as the earlier case itself. But what about the other edge, t minus 3? Here t minus 3 is also greater than 0. T minus 3 is also greater than 0. So this is the case which we are bothered about. T minus 3 is greater than 0 or t is greater than 3. Now we have, let us go back to the expression of y of t. In this case, now to compute the product from the graph, it is very clear that the product exists completely between t minus 3 to t minus 1. So the product is existing between t minus 3 to t minus 1. The rectangular pulse slowly glided through the to the right side. We have completely, it is totally inside the x of tau. I mean totally it is within the x of tau signal which is defined, but of amplitude 1. So now we have the limits as t minus 3. Now the product exists between t minus 3 to t minus 1 of amplitude 1 d tau. And on integrating and substituting the limits, we will get that it is 2. We get a constant 2. So this is how we have case 3, where the signal is totally moved to the right side. So it is completely moved completely to the positive values of t. So on consolidating all the answers in the step 5, we have y of t which is 0 for t less than or equal to 0. We have taken care of all the cases, that is it's 0 for t less than or equal to 0, that is when the signal the rectangular pulse was totally on the negative side. We have taken that, so we got 0. Then slowly gliding partly to the positive and partly to the negative, we got t minus 1. We got t minus 1, and completely shifting to the positive side, we got 2. And corresponding cases with respect to t, we have to write it with respect to t. So we have taken with respect to the edge t minus 1 and t minus 3. We have to consolidate the answers and bring it in the form of t when we are writing the uh, end result. So it is written in the form of t at the last. And as I've discussed earlier, it is very important to sketch y of t, the signal which is written in the mathematical form, we are going to sketch it. So it says that for all values of t less than or equal to 1, it is 0. So we have not drawn anything here. And between 1 to 3, it is t minus 1. T minus 1 is nothing but a ramp which is delayed by 1 unit. So we have delayed it between 1 to 3. And after for all values of t greater than or equal to 3, it is of a constant value which is 2. So here goes our y of t, which we have sketched when we convolve an infinite duration signal with a finite duration signal which happen to be a rectangular pulse. So we see the cases here are very, very different, and coming up with these particular cases are very crucial in solving any numerical on convolution integral. We have to go through very slowly so that gradually we glide it, and when you feel that there is a change in the product, those cases have to be taken into consideration. So here we see these are the important cases where the difference is actually seen, where the product changes and hence y of t changes. So these are actually the very important things which we have to think about and uh, come up with the cases. So this is the first numerical where we have convolved unit step with a rectangular pulse. The next one is a very important thing, is that we are going to convolve a finite duration with a finite duration. The complexity of the question is gradually increasing. The very first case in the earlier lecture we have seen infinite duration with infinite duration, which happened to be simpler with just two cases. Then in the last numerical we have seen finite with infinite, and now we are seeing a finite duration with the finite duration. So the question is defined where we are convolving two rectangular pulses. We have taken two rectangular pulses. So if we get this example very clearly, we can solve any other numerical of the same type. There will be no difficulty in solving. So let us see how we can go ahead doing this. So x of t is 1 between 0 to 2 and 0 elsewhere. So this happens to be a rectangular pulse between 0 to 2. It's a finite duration signal. And h of t is also a rectangular pulse between 0 to 1, 0 to 1 and 0 elsewhere. You have to observe that the pulse width is different in both the cases. X of t and h of t have different pulse widths. So let us take up this question. So as discussed earlier, we are starting with the definition of convolution. Y of t is equal to integral minus infinity to plus infinity x of tau h of t minus tau d tau. So this is our expression for convolution. So the basic primary step is to first sketch x of tau. We have sketched x of tau. So in the earlier slide we have discussed it's a rectangular pulse which is defined between the interval 0 to 2 and of amplitude 1 and 0 elsewhere. So we have changed to a dummy variable called tau and we have sketched the signal x of tau. So this is step 1. And in step 2, we are interested in sketching h of tau first. So h of tau is again a rectangular pulse but with a slightly shorter pulse width. So 0 to 1 and of amplitude 1. So this is our h of tau. Now what is interesting is that we have to come up with the basic operations of folding and shifting and multiplication and integration. So in that process, we will see how we can fold this signal and shift it. So on folding the signal h of minus tau, we have got on the vertical axis, we have got that this is 0 and this is minus 1. So this is what we have folded. Now here I have taken an important way of deciding the edges of this rectangular pulse by writing t for this and t minus 1 for this. So if I'm not shifting, if t is 0, this edge is 0 and this edge is minus 1. So I'm right in defining an expression t minus 1 and t for these edges of the rectangular pulse. I hope it's clear that we have defined that this edge is t and this edge is t minus 1. Like in my earlier case, how I have defined, now this edge is t and this edge is t minus 1. If I substitute t as 0, I should get back the same. I should get back my folded signal. I have got it back. If I substitute t as 0, I got back my folded signal. Now, we are interested in sketching h of t minus tau. So, we have to shift the folded signal. We are interested in shifting the folded signal, which is h of minus. This minus indicates that we are shifting the time reversed signal minus tau minus t. So the one within the bracket, the operation within the bracket says on the folded signal we have to delay it minus t. Minus t is telling it's telling us some value by which value we have to shift it. So we are interested in finding out h of t minus tau. So let us see how we can work on this. So I've called this edge as t and this edge as t minus 1. These are my two edges. If t becomes 0, I will get back this. I'll get back h of minus tau. I hope it's clear. If t is 0, I will get back h of minus tau. That's right. So t is 0, we will get back h of minus tau. Now let us take up the first case where t, that is this edge is less than 0. It is less than 0. If it is less than 0, we have to take up slowly, we are gliding it to the right side. So initially when t is less than 0, and when we have sketched both the graphs, both the signals on the same graph, we don't see a product which exists when t is less than 0. T is less than 0. See, this is 0 and this is the first edge. This is the edge. We don't see a product which actually exists in this case. We don't see a product. And that is the reason y of t is equal to integral minus infinity to plus infinity x of tau h of t minus tau d tau becomes 0, as we don't see any product which exists between these two signals, in which case that is t less than 0. We don't see any product which exists. This edge is still on the negative side, so we don't see any overlap or any product which actually exists. This is a very important thing, that is you fix up the edges is very important. And again I would like to summarize that when t is 0, when I'm not shifting at all, I will get back the folded signal, that is h of minus tau, which is very clear from these two graphs which are drawn one below the other. When t is 0, we get back h of minus tau. Right. So next case we will take up case 2, where I've slowly glided the rectangular pulse, and this edge, that is this edge which I had t, I'm fixing a limit that it is between 0 to 1. We are fixing a limit that this edge, the rectangular pulse edge, is between 0 to 1. So we have taken up between t is between 0 to 1. Now you will observe when we have drawn both the graphs x of tau and h of t minus tau in the same graph, you will observe that it has been, we have shaded this region between 0 to t, wherein a product exists between 0 to t. Only the region between 0 to t, we can say the product exists and of amplitude 1. And hence, we have determined y of t is equal to integral 0 to t, the product is only between 0 to t, 1 d tau. We say that it is 1 d tau. On integrating and substitution of limits, we will get it as t. That is case 2. So after slowly gliding the rectangular pulse, we will see that, see the arrowhead is written, the arrow mark is written. So we have slowly glided the rectangular pulse and we will see that there is a product which exists only between 0 to t. We have fixed up slowly, we can't just randomly put the t somewhere here, because when I am gliding, I should also bother about the width of the pulse. So here it is supposed to, it is, if it's between 0 to 1, I can fix a value of t as somewhere as 0.5. If one edge is at 0.5, the other edge, that is t minus 1, will be on the negative side, because the width of the pulse here is nothing but, it is of 1 unit. Width of the pulse is 1. So this might be somewhere around minus 0.75. So this edge has to be fixed. So that is the reason we have to give some numerical value and analyze the edge where it is, fix the edge and then slowly glide it. So this is between 0 to 1. The next case is that we have slowly glided the rectangular pulse which is of width 1. This edge t, we are fixing the position between 1 to 2. Earlier it was between 0 to 1. Now I have fixed between 1 to 2. You see that this t is between 1 to 2, 1 to 2, and when we fix it up, that is between 1 to 2. For example, I have written within green color, written in green color, just for me to come up with a better understanding, that if the t is between 1 to 2, I've given a value say 1.5, the other edge, the width of the pulse is actually 1. That will not change. The other edge will be at 1.5 minus 1, which is nothing but 0.5. The other edge will be between 0 to 1. So we see that the other edge is somewhere between 0 to 1. This will not change, 0 to 1. So the other edge apparently falls between 0 to 1. So that is the reason t minus 1 comes here. So you can interpret better when you give some numerical value, and then you can comprehend the where the rectangular pulse will actually fall into. The width of the rectangular pulse should be always kept in mind. We just like that can't glide it. The width of the rectangular pulse has to be kept in mind, in view, and then the edges are fixed. So this is 1.5. So the next edge is at 0.5. Of course, this is only for our understanding, but the edges are t and t minus 1. And you will observe that it has been highlighted in green, that we will see the red color is nothing but the glided pulse, that is h of t minus tau. The blue color pulse is the x of tau. And you will see that there is a product which actually exists. Yes, there is a product which actually exists. But what are the limits of the product? The product exists between t minus 1 to t, because this is the width of the rectangular pulse and this is where our product actually exists. So in our integral also, our limits t minus 1 to t, the limits change to t minus 1 to t. You have to observe the difference from the earlier case, case 2 and case 3. The limits will keep changing. T minus 1 to t, 1 d tau. On integrating and substituting the limits, that is 1 d tau, we get tau t minus 1 to t. On substituting the limits, we will get a constant 1. So the rectangular pulse between 1 to 2, we got the answer as 1. We have not completed with the cases. We have to bother about all the values of t. Though it is completely within the rectangular pulse, we still have couple of cases to be discussed. Now we will slowly glide it little more and bring it to 2 to 3. Case 4. Earlier it was between 1 to 2. Now we have brought it to 2 to 3. Now you will observe that the T, this edge of T, that is the red color pulse which we have, this was our h of t minus tau. We have fixed it between 2 to 3. We have glided it little more between 2 to 3. So if this edge happens to be 2.5, between 2 to 3 I've taken a value as 2.5. The other edge 2.5 minus 1 will be 1.5. The other edge will be between 1 to 2. We have the other edge between 1 to 2. So the other edge, you see the other edge is between 1 to 2. Here we have 1 to 2. You can see here. This is 1 to 2. So if we have t here, we have t minus 1 here. This is just to give you a better understanding. I have taken these numbers. You can skip if you want, but what matters is this t minus 1 and t. Now again the width is still 1. This has to be ensured in each and every step. Now what happens when we when we glide it and fix the edges between 2 and 3, when the t is fixed between 2 and 3, where does the product actually exist? The product actually exists only in the limit t minus 1 to t. We see that it is actually existing only between 2 t minus 1 and 2. You see that this is where it is actually existing. So that is why we have shaded this particular region. Elsewhere it is 0. The signal is not defined. So it is existing only between t minus 1 to t, and of course with amplitude 1. So the limits in this case have again changed. So it is between t minus 1 to t to 2 and amplitude 1 d tau. On integrating and substitution of limits, we will get that it is 2 minus t plus 1. So it is 3 minus t. 3 minus t is what we have got. The answer for the case between 2 to 3. 2 to 3 we have got this as the answer. So very interesting one, that we have kind of shifted the rectangular pulse to the right side. Still we have not concluded. The rectangular pulse has to be totally shifted out. So both the cases, on the left side and the right side, we have to ensure that the signal, there is no product, or totally moved on the left side and on the right side. So on the right side we have glided it. We still have not completely shifted the signal out, so that we have to bother in the next case. So case 5, we have taken that earlier case we have taken that it was between 2 to 3. T was between 2 to 3. Now we have taken that T is greater than 3. So if I fix it up, T greater than 3, this is our edge. This is our h of tau, where we have fixed it as 3.5. If it's greater than 3, where will the other edge be? 3.5 minus 1 will be 2.5. This is our 2.5. Now if it is 2.5, do you see any product which exists between this x of tau, which is actually defined between 0 to 2, and h of t minus tau? We actually don't see any product which exists between x of tau and h of t minus tau. There is no product. So the t here is actually greater than 3. This edge is greater than 3. So it could be anywhere. For simplicity, I have taken 3.5. If it's 3.5, the other edge is actually 2.5. So we don't see any product which actually exists. So hence y of t will become 0. Y of t is 0. So the signal on either sides, we have taken care that either sides, that is on the positive side and as well as the negative side, both the cases we have ensured that the signal was actually totally shifted out and all the cases were being taken care. So there ends this question where we have seen that the product is not existing here. So consolidating all the cases, we will get, that is that edge which was on left side when t was less than 0, we observed there was no product. Slowly gliding the t between 0 to 1, we got t. Between 1 to 2, we got 1. Between 2 to 3, we got 3 minus t. And then completely moving the signal, shifting the signal to the positive side, completely moving it out. we didn't observe any product, and hence again we got 0. So this first case and last case, we will get to know that we have come done it correctly or not by moving it slowly. We will not observe any product, and hence we will get the answer as 0. So this has to be checked, and this is very easy provided you take case by case, slowly glide it on taking up case by case. That will be a very interesting question, and you can come up with the correct answer. So let us sketch this waveform y of t. So for t less than 0, obviously it is 0, and for between 0 to 1, you can just check for the equality sign here and eliminate here. That you can take care. So this is t between 0 to 1, it is a ramp, 0 to 1. Between 1 to 2, it is 1. 1 to 2, it is of amplitude 1. Between 2 to 3, it is 3 minus t. 3 minus t. 3 minus t is a ramp signal which is folded and time shifted. So we have folded. So when you take a ramp, if you fold it, it will come this side, and then it is delayed by 3 units. So there goes the other side of this signal, 3 minus t and 0 elsewhere. So if you observe, this is a very standard result, which you have to think about. When you convolve two rectangular pulses of unequal widths, we had two unequal widths, we will end up getting a trapezoidal signal. Output is a trapezoid. So that is where we get y of t as two signals. That y of t is a trapezoidal signal when we convolve two rectangular pulses of unequal widths. So I hope you have understood how we have gone about convolving an infinite duration with a finite duration, a finite duration with an finite duration with a finite duration. So a very complicated case is when you have to convolve a finite with an infinite. You will observe many number of cases, and you have to ensure that you have taken up all possible cases, then only your answer will be right. So to the end of this lecture, I would like all of you to solve a question by taking two rectangular pulses of equal width. That is, you will be taking a width of 1 between defined between 0 to 1, 0 to 1. Both the pulses are of width 1, and both the pulses are defined for defined between 0 less than or equal to t less than or equal to 1 and 0 elsewhere. And I want all of you to sketch y of t and comment on the result. So this is the question which has to be done after this lecture. The convolution of a rectangular pulse with itself. This is the question. And the width of the pulse is 1, and the time duration is between 0 to 1. It is defined, the pulse is defined between interval 0 to 1. Thank you.